Welcome to Found in Space, a science podcast for kids and teens. Nadia asks, how does the glass for a telescope help you look all the way into space? So, Nadia, this is a wonderful question because it really gets at the heart of astronomy, which is observing the universe and trying to understand it. And telescopes are the main way that we can study anything beyond Earth. So, here on Earth, if you want to know about how a particular rock formation happened or the effects of tides or things like that, you can go and look at them. But in order to see what's happening between stars or black holes or on other planets, those are harder for us to access. So we need telescopes for that. And essentially, what a telescope is a light collector. So it seems like this question is really getting at how do telescopes work? So light carries information. When I look at something, I can tell the color of it, which might give me a clue as to what it's made from. I can see the shape of it because we have two eyes. We can actually tell how far away or how close something is to us. So there's a lot that we can learn with light. So the more light we collect, the more information we have. And that's what telescopes are really about. So there are two main types of telescopes. They both serve the same purpose, collect the light, but they do it in a little bit of a different way. So the more light you collect, the more information. So the bigger your light collecting area is, the more information you're going to be able to collect. But we need to concentrate that light into one place. You can imagine it kind of like a funnel, like the funnel you might use in the kitchen. Let's say you have a big amount of liquid and you want to pour it into a small container. You'll take that little tool that is big at the opening and small at the exit for it. So telescopes are sort of like that. So our first type of telescope is called a refractor. And this is the kind of telescope that Galileo used. Galileo is often credited as being the inventor of telescopes. Now, he probably wasn't. It's a pretty interesting story, but there's several different people who were working on telescopes around this time, so back in the early 1600s. But we do know that it really was Galileo who was the first to take a telescope and point it at the sky and record what he saw. Other telescopes at the time were being used as spyglasses for ships and to see what was far away. So it'd be very useful if you were in a navy to see what ships were on the horizon that the human eye couldn't see. But Galileo, he pointed it at the sky. Now, refractors, they basically work the same way that our eyes work. They have an area that collects light. Now, for us, that would be our pupil. So the black part in our eye is the part that is getting the light. So the light is literally going through that hole. The pupil is a hole, and the part that has color, that's the iris. So the brown or blue or green or whatever color your eyes are, those are muscles that control how big the hole is, that pupil. The bigger it is, the more light it lets in, which is why at night or in a dark room, our pupils are really big. And the smaller they are, the less light it lets in. So if you go out on a bright day, your pupils are going to be really small because your eyes are trying to protect themselves from getting too much light. Well, with a telescope, you'll notice that telescopes, they're usually several inches across. A typical telescope might be almost three, so about 2.75 inches or maybe 70 millimeters across. And that's going to collect a lot more light than just your little pupils. So you can collect a lot more light that way. Now, right behind our pupils, there are lenses. These are clear, they're little almost disc or plate shaped structures that when the light passes through, the light gets bent slightly. They get refracted. The light is refracted. And if you look at a telescope, it has the same thing. It's got a lens there. Same thing as if you look at a pair of glasses or a camera, those have lenses too. So the job of the lens is to redirect the light. Remember, we were talking about that funnel analogy? So this is the entrance to the funnel, and now the light is going to be directed down the barrel of the telescope to the back of the telescope where there is the receiving piece, the eyepiece. Or in a lot of modern telescopes, we might have a camera set up there. Now with our eyes, that goes to the back of our eye, called the retina, where there are these special structures called cones and rods that are activated when they're hit by light. Either way, the eye and the refractor work the same way. They collect a bunch of light and then they concentrate it into a small point where it can then be received. With our eyes, it goes to our brain. With a telescope, it's going to either go onto our eyes or a camera, and then we can look at that picture and we can get information about it. Now, there's a second kind of telescope, and these are reflectors. So reflectors don't use lenses. Light doesn't pass through a glass lens. What happens instead is that the light falls onto a big reflective surface. Now, if this is a visible light telescope, like most telescopes that you'd think of, it's going to be a mirror. And that mirror has a very gentle curve to it. It's almost like a very shallow bowl. And so when the light hits it, it doesn't bounce straight back out because the mirror is curved. It is actually directed to another mirror. And then that mirror bounces it to an eyepiece. That's where we're collecting the light. So it's the same thing as the funnel. It's just we're bouncing the light around instead of bending it like we do in refractors. Now, reflectors, this is the type of telescope that tends to be made really, really big. So some of the huge telescopes that are made by agencies like NASA or ESA is the European Space Agency, these are going to be reflectors because it's a lot easier to make a big mirror than it is to make a big lens. If there's anything that isn't quite perfect about your lens, it's going to mess up the image. If you wear glasses, or maybe if you've worn goggles before when you're swimming, or sunglasses, and something gets on that lens, then you've got like a smudge in your vision. It makes it really difficult to see. So we don't want that to happen with our observations. So our big telescopes are going to be made with mirrors. Now, here's where it gets really exciting. There's actually different kinds of light. Humans, we see what we call visible or optical light, and that is the rainbow, right? We see all the way from red. So we see red, orange, yellow, green, blue, and violet. And we don't really see very much violet. Violet is like a bluer version of blue. So often we just talk about red to blue. But those are the colors that we see. But there are colors which are invisible to human eyes that other animals see. For instance, ultraviolet, which you may hear called UV, some types of insects and birds can see a little bit into ultraviolet. They can see colors that are invisible to us. So those are colors that are bluer than blue. Now, beyond ultraviolet, there are other types of colors as well. X-ray is actually light. Yeah, so X-ray, the same thing that you might have gotten if you went to the dentist to check if you have any cavities or if you ever broke a bone, that is actually light as well. And beyond, even bluer than X-ray, are gamma rays. Now, gamma rays, X-rays, and ultraviolet, we have to be careful because those are ionizing forms of radiation. So visible light doesn't really hurt us, but if you get too much UV or too much X-ray, it can be harmful to us. So good news for us is those types of light are actually blocked by our atmosphere. So lots of that light is coming from the sun, coming from other stars and supernovae and things like that. but very little of it actually gets down to Earth. And that's one of the jobs of the ozone layer, is to block some of that ultraviolet radiation. Now, on the other side of the rainbow, red, if we have a color that's even redder than red, that's also invisible to us, but it's still light. It's just our eyes don't see it. So colors that are redder than red are infrared. And even redder than infrared, we get to microwave. Microwave light is the type of light that, yes, we use in microwave ovens in really, really intense concentrations, but it's also the type of light that we use for Wi-Fi and for things like cell phone or mobile phone calls. And even redder, even longer wavelengths than that, we get to radio. So radio waves are actually light as well. But they pass through things like the walls, mountains, cars, buildings just fine. Whereas the shorter or bluer light, they can't do that as well. So going back to the beginning, we said that light is information. So there's a lot of information in these colors that our eyes don't see. So we figured out how to build telescopes, which are reflector telescopes that can catch these types of light. And then we have to use computers to help us process that because we don't see it. But we can then shift those colors. Once we put it into a computer, we can map them to colors that we can see, so we can take images with these other types of light. But I said that some of these lights don't make it through the atmosphere, right? That air blanket that surrounds the Earth. So in order to be able to use those types of light, we have to take our telescopes and actually send them into space up above the atmosphere. So that's one of the reasons that the James Webb Space Telescope or the Hubble Telescope or other very famous ones like Spitzer are so amazing, is because they're up above our atmosphere and they can use different types of light to actually observe the universe. And they don't have to worry about the light getting kind of blurred and distorted as it comes down through the atmosphere. So we've got a lot of amazing telescopes here on the Earth and a lot of amazing telescopes that are actually up in space. And in the future, we're going to talk more about these different telescopes. For now, though, this is a pretty good place to pause. If you listening have any questions about space that you would like answered on the podcast, go ahead and have your grown-ups help you send an email to the email in the description box. So there's information there on how to send your question in. And as always, thank you so much. I hope you have dark skies, and I can't wait to talk about space with you next time.